Before we start today's episode, I just wanted to make a quick announcement, namely that the 6th volume of the book series based on the podcast is now out. This book is available from Oxford University Press and is called A History of Philosophy Without Any Gaps, Byzantine and Renaissance Philosophy. It offers revised versions of the scripted episodes from those two series, with additional references and a lovely cover in imperial purple, as befitting the many rulers named Constantine mentioned in the first half of the book. While we're at it, I'll also mention that all 5 of the previous volumes are now available as paperbacks. So please consider taking this opportunity to imitate a Renaissance humanist and build up your library. If you buy them from an independent bookstore, so much the better. Now on with the show. Hi, I'm Peter Adamson, and you're listening to the History of Philosophy podcast, brought to you with the support of the Philosophy Department at King's College London and the LMU in Munich, online at historyofphilosophy.net. Today's episode, The World Doesn't Revolve Around You, Copernicus. We are used to the way scholars try to complicate, nuance, and correct popular conceptions of historical figures and events. We're not really sure about Luther nailing those theses to the door, and if he did, it wasn't that unusual. The Holy Roman Empire was neither holy nor Roman nor an empire, and speaking of Rome, fiddles hadn't even been invented when Nero watched it burn. But I don't recall covering any figure in this podcast where the expert and non-expert stories drift so far apart as they do in the case of Nicholas Copernicus. For the layperson, it's almost too good to be true that his great work on astronomy was called On the Revolutions, because that's just what he was, a revolutionary, who set out quite literally to overturn the ancient and medieval worldview and replace it with something more scientific. He was a rebel against not just existing science, but also the church, which bitterly opposed his discovery. He was, in short, a champion of reason against authority, and his breakthrough amounted to the most important harbinger of the Enlightenment. In the scholarly literature on Copernicus, by contrast, we find a far less iconoclastic and more historically plausible figure. Far from being a rebel against the church, he dedicated On the Revolutions to the Pope. Soon after its appearance, Catholic bishops were involved in disseminating the book. Copernicus himself was a Catholic canon who maintained his confession despite having close working relationships with Protestants. The papacy did not officially condemn Copernicanism until 1616, the better part of a century after Copernicus's death in 1543. Indeed, there was little reason to condemn it, in part because astronomy, unlike astrology, was as yet not a theologically provocative discipline, in part because so few people were convinced by it during that time. As the Copernicus scholar André Godou has commented, his efforts to persuade Aristotelians have to be counted in the short term among the most miserable failures in the history of philosophy. So, if this was an explosive scientific revolution, it was one whose fuse took a long time to burn, requiring figures like Galileo and Kepler to fan the flames around the turn of the 17th century. More importantly, for understanding Copernicus's own project, a reading of On the Revolutions itself, never mind the scholarship devoted to it, makes it clear that this is not an irreverent attack on established authority. To the contrary, the work situates itself within the tradition of the most important astronomical text of antiquity, the Almagest of Ptolemy. Copernicus praises his predecessor and presents himself as addressing problems and anomalies that he finds in the Ptolemaic system, not as replacing that system with something else that is radically new. His admirers framed Copernicus's project in the same way. His student, Georg Joachim Rheticus, said that for his master, there was nothing better or more important than walking in the footsteps of Ptolemy. This was perhaps laying it on a bit thick, but it's plausible when Rheticus goes on to say just afterwards that Copernicus did not reject the teachings of the ancients in a lust for novelty, but only for good reasons, and when the facts themselves coerce him. Another bright star in the firmament of the new science, Kepler, said that Copernicus basically believed in Ptolemy's ideas about astral motion and wanted to show how the observed phenomena could be made to fit. Modern research has broadly confirmed this, showing that Copernicus put the sun in the middle of the cosmos and made the Earth one of the planets orbiting it because he was trying to save features of classical astronomy that he thought were more important than geocentrism. In particular, he believed that the universe should be a harmonious unity whose most outstanding parts are heavenly orbs, which revolve in perfect uniform circles, just as Aristotle and Ptolemy had assumed. When I say orbs, I don't mean the visible planets. I mean transparent rotating spheres on which the planets are seated, like shining diamonds embedded in spinning fishbowls. These spheres are laid on top of each other concentrically, like a dartboard with a bullseye, but in 3 dimensions. Their perfect rotation carries the planets around, yielding the motions studied by astronomers. Copernicus also retained the Ptolemaic idea of an epicycle, meaning a smaller rotating sphere within and carried along by the larger sphere. You can imagine that the rotating fishbowl has a spinning glass marble embedded in it at some point along its circumference, with a diamond in the marble. In other words, the planet is seated on an epicycle, which helps to explain why its observed motions are more complicated than they would be with one circular motion around the bullseye, that is, the center of the universe. And it is here, of course, that Copernicus departs from Ptolemy. The latter, and almost all ancient and medieval theorists, we'll get back to the almost part, believed that the celestial spheres were rotating around an unmoving Earth. But Copernicus, of course, said that the sun is at the center, or actually near the center. Only the moon orbits the Earth, while the Earth is a planet, and like the other planets, goes around the sun. How did Copernicus arrive at this bold claim, which seems to be refuted by our everyday experience? As you might almost expect, there is disagreement over that question. On the Revolutions itself is not the most obvious place to look for an answer, because it was published only at the end of Copernicus's life, quite literally. A famous anecdote has the freshly printed pages being shown to him on his deathbed. An earlier work, the Small Commentary, was written at some point before 1514, but never printed. Only 3 manuscripts survive. In this little treatise, Copernicus simply sets out 7 assumptions, including the idea that the Earth is moving around the sun once a year and revolving on its own axis once a day. Rather than broadcasting this dramatic thesis as widely as possible, Copernicus only circulated it in the form of handwritten copies among friends and interested colleagues. Only in 1540 did Rheticus publish Copernicus's findings in a text called the First Report, with On the Revolutions following 3 years later. All of this means that we need to work backwards to figure out the thought process that led Copernicus to his breakthrough. One factor seems to have been his rejection of the so-called equant, a clever technical device invented by Ptolemy. The idea here is that the planetary spheres, the fishbowls in my analogy, revolve not around their own centers, where Ptolemy would locate the Earth, but around an off-center point in space. This, combined with epicycles, yielded a mathematical construction that could fit the heavenly motions, explaining why they seem, from our point of view, to speed up and slow down during their orbits. But, as readers had been noticing for quite a long time, the mathematical model involving an equant seems in flagrant contradiction with the physical model of concentric spheres centered on the Earth, rotating serenely around that center. Another issue that may have motivated Copernicus was that, in the words of the earlier Renaissance astronomer Georg von Feuerbach, all the planets share something with the sun in their motions. In particular, astronomers had noted that the retrograde motions of Mercury and Venus, that is, the times where they seem to go backwards from our point of view, track the motions of the sun. This is a lot easier to explain if you say that they're going around the sun and not the Earth. It happens because the Earth is catching up with and then overtaking the inner planets relative to the sun. As Copernicus notes in On the Revolutions, since the time of Ptolemy himself, there had been disagreement over where to put these 2 planets in the celestial order. Some thought that they were between the Earth and the sun, while others put the sun closer to the Earth, followed by Mercury and Venus, and then Mars. Here we come to another possible divergence from the popular conception of Copernicus. It's been argued, especially in a controversial book by Robert Westman, that Copernicus was especially worried about the order of the planets because this question is vital for astrology. Westman provides circumstantial evidence that, during his youthful student years in Italy, Copernicus fell into the orbit, if you'll pardon the expression, of the Bologna astrologer Domenico Maria Novara. He would have been one of the prognosticators working together with Novara, who were keen to rebut the attack on astrology mounted around this time by Pico della Mirandola. Unfortunately, the evidence for his connections to Novara is pretty thin, and Copernicus never talks about astrology as a context for his ideas. If you like the notion of an astrologer Copernicus, though, you could find a ready explanation for that. His ultimate inspiration was Ptolemy's Almagest, which was devoted to mathematical astronomy, not astrology. But Ptolemy was also an astrologer. He wrote an entire treatise on the topic called the Tetrabiblos. So Copernicus's failure to discuss this art could simply be a matter of genre. He may have believed in astrology without believing that On the Revolutions was the appropriate place to discuss it. Furthermore, his student Rheticus was definitely interested in astrology. In short, there's no reason to suppose that Copernicus would have seen astrology as unscientific, and some reason to suppose he was interested in it. While this remains a matter of speculation, there is no doubt that establishing planetary order, and in particular giving a good reason for the planetary order, was a matter of central importance for Copernicus. He may have flirted for a time with a construction like the one later accepted by Tycho Brahe, according to which some planets revolve around the Sun, while the Sun revolves around the Earth. By the time of the Little Commentary, though, Copernicus is clear that the Sun is at the center of the universe, while the Earth is a planet. Again, physical considerations may have been important here, because the compromise view could have led to celestial spheres competing for the same space. A mathematician wouldn't mind having overlapping circles in a diagram, but in natural philosophy, we don't want overlapping cosmic fishbowls. Most compelling, though, must have been Copernicus's discovery that it would be possible to arrange all the planets, including Earth, at successive distances from the Sun, with their ordering correlated to the time of the period of the orbits of the planets. In other words, the closer a planet is to the Sun, the shorter the time it takes for the planet to make one trip around the Sun. While that is a powerful argument in favor of heliocentrism, there were also a number of objections for Copernicus to face. The most obvious is this: why do we feel like the Earth is at rest if it is, in fact, moving in two ways at all times, both around the Sun and around its own axis? Actually, he also introduces a minimal third motion to keep the axis of the Earth pointing in the right way as it goes around the Sun, but we don't need to get into that. In response, Copernicus quotes a line from the ancient Roman poet Virgil, which talks of how the land slips backwards as a ship leaves port. To an observer in motion, what is at rest may seem to be moving, and what is in motion may seem to be at rest. Just as passengers on a ship feel as if the ship is standing still while the coastline moves away, the heavens seem to be turning over the Earth, but actually it is the Earth that is in motion. This point had already been made by 14th century thinkers like Peter Oriol, even using the similar example of people traveling down a river and seeming to see the trees move while their boat is apparently at rest. And if this sounds familiar, it's because I mentioned it in episode 275. So, actually, the answer to this apparently fundamental difficulty was quite easy to give. More difficult were certain technical issues of astronomy and natural philosophy. On the astronomical side, there was a problem that had to do with the outermost sphere housing the so-called fixed stars in it, that is, all the stars that are not planets. If it is at rest, and the Earth is moving around the Sun, shouldn't we see them shifting in the night sky, even if only a little, because we are looking at them from a changing position? This phenomenon is called parallax, and its absence was indeed a real mystery for Copernicus. He gave the correct answer, namely that the universe is a lot bigger than commonly thought in the previous scientific tradition. Since the fixed stars are so far from us, the change in angle of view is tiny, and there is no difference in their observed position. Centuries later, the parallax was actually measured using better instruments than those available at the time, confirming that Copernicus had been right. And by the way, don't forget that Copernicus does not have the benefit of a telescope for any of this. That comes in only with Galileo a couple of generations later. As for natural philosophy, a major obstacle here had to do with something else we can see every day, things like stones falling to the ground. In Aristotelian physics, heavy things that are dominated by earth and water move toward the center of the cosmos, while light things dominated by fire and air move away from it. Since the center of the cosmos is also the center of the Earth, This nicely explains why rocks fall straight down and flames flicker upwards. How can Copernicus offer a superior rival explanation? Basically, the answer is he can't. For that, we'll need to wait for 17th century physics. He does his best, though, proposing that God implants a natural desire in each element to move towards the place where the whole of that element gathers. As Copernicus notes, the result will be that a falling rock actually moves in a far more complex way than we would suppose. It is moving straight down toward the ground, but simultaneously also in a circle, being part of the planet Earth. More compelling, at least within the historical context, is his explanation of why the Earth is revolving in the first place. He reminds his readers that, for Aristotle, it is natural for spherical things to move in circles. This is, after all, why the celestial orbs are rotating. Wouldn't it make sense, then, that the Earth also moves in a circle, given that it is spherical? While it may seem a little disconcerting that the Earth has more than one such motion, this is actually typical of planets, which, as we saw, are moving on large orbs and also on epicycles within those orbs. These arguments give a flavor of Copernicus's attempt to show that heliocentrism could make sense within a broadly Aristotelian worldview. While this attempt was, as already noted, a miserable failure, it does reinforce our sense that Copernicus wanted to revise the science of his day, not reject it wholesale. To which you might object that this could simply be a rhetorical ploy. He wouldn't be the only revolutionary in history to pose as a moderate reformer. I don't think this is right, if only because, as we've been seeing, he retained many features of the Aristotelian Ptolemaic cosmology, and was apparently even motivated by the desire to show how those features could be maintained. And that doesn't mean there is no rhetoric in On the Revolutions. To the contrary, this is a text bearing marks of the humanist movement that was so dominant in his age. That quotation I mentioned from Virgil is only one of numerous allusions to classical sources. He also uses an analogy which scholars have connected to a passage from Horace's Art of Poetry, which compared bad literature to a monster made out of spare parts. This Frankenstein-like image is used by Copernicus to complain of the disorderly cosmos depicted by other astronomers. Another striking case is a citation from Plutarch, who reported that, for the ancient Pythagoreans, the Earth moves around a central fire. This fire is apparently not meant to be the sun, but still, it looks like a nice anticipation of Copernicanism, which is why I said earlier that almost all ancient and medieval cosmologists had been geocentrists. It's also been shown that Copernicus borrowed ideas about elemental motion from the Platonic tradition. John Philoponus had spoken of the elements moving in order to return to their holes. A more approximate inspiration from the history of Platonism, or at least a comparison, given the lack of any evidence of historical influence, would be another Nicholas of Cusa. The Copernican true believer Giordano Bruno asserted that Copernicus was saying more audaciously what Cusanus had already affirmed with a lower voice in the book On Learned Ignorance, and there is at least some truth to this. Cusanus had also argued that the world was possessed of enormous size, beyond what was admitted by the scholastics, and as we saw back in episode 374, he allowed for motion of the Earth. He even made the point that we fail to notice this motion only because we are on the Earth and thus moving along with it. A further link to Platonism, whose significance has been greatly stressed by the aforementioned André Godot, has to do with Plato himself. We have a copy of Plato's Parmenides with an annotation in Copernicus's own hand. For Godot, this suggests that Copernicus took inspiration from Plato for his use of hypotheses in science. Hypotheses are a major structural feature of Plato's Parmenides, but they would also have featured in Copernicus's education. As I mentioned, he studied in Italy as a youth. He had been at the University of Krakow, but left without getting a degree to study law at Bologna and then medicine at Padua. Ultimately, he got his degree in church law from Ferrara, setting him up to work for the church as a canon at Warmia in modern-day Poland, beginning in 1503. In Warmia, he encountered a number of humanists in the Erasmian style, not least Tiedemann Giese, who supported Copernicus and would later encourage the publication of On the Revolutions. Copernicus resided in the bishop's castle at Litzbach, acting as the bishop's personal physician from 1503 to 1510, when he moved to the cathedral at Fromburg. While he would remain active, carrying out various duties as a canon, This date seems to mark the end of his prospects of becoming a bishop himself. The church's loss was science's gain. Given this formation, we can say that Copernicus had training in several of the chief university disciplines of his day, as well as contact with humanist circles. Certainly, he was first and foremost a mathematician who said that On the Revolutions was written for other mathematicians like himself. The title page of the printing even features the slogan that was emblazoned outside the Platonic Academy, "Let none ignorant of geometry enter." But he was a well-rounded 16th century intellectual, not just a mathematician, and used the tools of rhetoric and dialectic in presenting his daring astronomical ideas. And perhaps also in discovering those ideas. Godot argues that Copernicus put to use ideas about hypothetical reasoning, which can be traced ultimately back to Plato, and which I might add were being discussed around this time by Zabarella and other Averroists at Padua. This method is most clearly on show in the Little Commentary, where, as we saw, Copernicus lays out 7 principles, whose viability seems to be confirmed by the satisfying results that follow from them, notably the aforementioned correlation between the periods of the planets and their ordered distance from the Sun. We can take a similar conclusion from the preface to On the Revolutions, where, having made his accusation that the geocentric astronomers make the cosmos into a monstrous patchwork, he says, "This would not have happened to them had they followed sound principles, for if the hypotheses assumed by them were not false, everything which follows from their hypotheses would be confirmed beyond any doubt." Now, on the face of it, this is hardly an advanced insight. Bad assumptions lead to bad conclusions. But on André Godot's telling, at least, Copernicus's methodology was quite a bit more sophisticated than that. It involved doing what Plato does in the Parmenides, namely setting up a series of hypotheses and testing each of them, both negatively and positively. For instance, see what follows if the Earth is in the center of the cosmos. See what happens if it is not. If it is in the center of the cosmos, we get the disordered monster of the Aristotelian Ptolemaic system. If it is moving around the Sun, we get nice outcomes, including the avoidance of Ptolemy's clever but physically awkward device of the equant. For the sake of exposition, the favored hypotheses or axioms are presented at the beginning of the discussion, but they are not simply stipulated at the beginning before doing any scientific inquiry. Rather, they have proven their worth by being tested for their results. Hypotheses are like Johnny Appleseed or like slot machines. By their fruits you shall know them. Godot puts it in somewhat less jocular terms, writing that Copernicus arrived at the postulates initially by means of a dialectical exercise, identified conclusions, formulated the postulates that he needed to derive the conclusions, and then reorganized them. This is relevant to one of the most hotly debated questions concerning Copernicus's new astronomy. How seriously did he mean it? Or better, in what sense did he seriously mean it? In pre-Copernican cosmology, we often find proposals that seem to be purely mathematical constructions, with an unclear relationship to what is physically going on out in the heavens. Ptolemy's equant would be a prime example. It may seem clear from what we've learned in this episode that Copernicus did not intend his system to be taken in that sense. He gets into natural philosophical questions like the motion of the elements, worries about problems like parallax, and so on. So obviously, he did not just mean that the math works better if you imagine the Earth going around the Sun. He meant that the Earth really goes around the Sun. But for initial readers, that impression was undermined by an unsigned address to the reader added to On the Revolutions. Written by Andreas Osiander, it suggests taking the heliocentric system as merely hypothetical, rather than as a true account of the causes lying behind our astronomical observations. The addition of this brief address has been outraging partisans of Copernicus since its initial publication. Rheticus crossed it out in his copies of the text. Subsequently, it was made part of the cliched story that has rational science being opposed by the religious establishment. At the end of the 19th century, a work with the frank title A History of the Warfare of Science with Theology in Christendom condemned Osiander in the following terms. Osiander's courage failed him. He dared not launch the new thought boldly. He wrote a groveling preface, endeavoring to excuse Copernicus for his novel idea, and in this he inserted the apologetic lie that Copernicus had propounded the doctrine of the Earth's movement not as a fact, but as a hypothesis. Thus was the greatest and most ennobling perhaps of scientific truths forced in coming before the world to sneak and crawl. Poor old Osiander has since found defenders, though. While he was interested in astronomy, his real calling was biblical humanism. He was a leading reformer at Nuremberg, whose decision to leave his name off the preface makes good sense given that this was a book by a Catholic dedicated to the Pope, albeit one printed by a Protestant publisher. When he suggested reading the theory as mere mathematical hypothesis, he was trying to help by offering a way that skeptics could find it palatable and useful. Furthermore, there are some claims on the revolutions that should arguably be taken in just the way that Osiander suggested. Copernicus points out that one can introduce eccentric spheres, that is, great orbs whose center is not at the midpoint of the cosmos, instead of epicycles, and get the same mathematical and observational results. He admits that, therefore, it is not easy to decide which of them exists in the heavens. This is not to say that something as fundamental as his heliocentrism is being offered as a mere hypothesis, but it is to say that hypotheses play a role throughout his method. Some of them are effectively confirmed or disconfirmed by their consequences, this being the fate of heliocentrism and geocentrism, respectively. Some, though, may remain merely likely or useful. The ultimate compliment to Osiander has been paid in modern times by the great historian and philosopher of science Pierre Duhem, who died in 1916. He emphasized the realist elements of On the Revolutions rather than the hypothetical ones, and said that this was a weakness of the work. Scientists should think of their theories as provisional hypotheses that remain open to revision. In a similar vein, Osiander explicitly stated that scientific constructions may be intended as purely instrumental or heuristic devices. Thus, he wrote that Copernicus's hypotheses need not be true, nor even probable. On the contrary, if they provide a calculus consistent with the observations, that alone is enough. But of course, the wider context here was very different from the one in which Duhem was working. Osiander's portrayal of astronomy had to do with his commitments as a fervent Protestant. Only revelation offers certain truth, and human reason must make do with making better guesses instead of worse ones. No wonder then that this scientific approach came to be associated with the reformers at Wittenberg. There, Philip Melanchthon urged his young students to engage in science, including astronomy, while remaining conscious of the limits of merely human knowledge. This was one of several developments that conditioned responses to Copernicus and ensured that his revolution remained, for now, a quiet one. We'll talk about this more next time, as we lay the background for the work of Tycho Brahe and Johannes Kepler, central characters in the story of the world's being knocked onto its axis. Let's meet back here for that after 14 more revolutions on the history of philosophy without any gaps.